Hello, and welcome to Physics Today. We're going to be looking at circular motion. And at this point, hopefully we have a good idea of two-dimensional motion. We know how to separate things into horizontal and vertical, and we know how to decide where projectiles are going to land, how high that they're fired from, and how fast they have to be fired in order for them to reach that point. But like I said, today we are talking about circular motion. So the first thing I want to do is define the difference between rotation and circular motion. Rotation is when we have an object spinning on an axis. For example, this lucky cat. Notice that all parts of the cat are rotating at the same speed. It's not like the ears are rotating faster than the tail or than the head. It doesn't matter where on the cat it is, the whole cat is rotating as one object. It is spinning on its axis. Other examples of rotation include the Earth rotating on its axis or a basketball spinning on a player's finger. Again, those notes about rotation. Rotation is occurring at the same speed everywhere on the cat at the same time. On the Earth, it's not as though people on the equator rotate faster than the people at the poles. Everyone rotates together because we're all on the same planet that's all spinning at the same speed. How do we define that speed? Well, rotation, we use the term radians per second or revolutions per minute. Radians per second is what you'd use in higher level physics, but in terms of everyday conversation, you've probably heard RPMs. If you haven't, look on the instrument panel of a vehicle and you'll see RPMs as those cylinders rotate so many times per minute. It is important to notice that no matter where you are on the cat or on the earth or on the basketball, everything has the same RPMs or radians per second because it's all spinning at the same speed. Alternately, we have circular motion. Here, this bird is going in a circle around this cup of coffee that's being stirred. This bird is not rotating. It is moving with speed. It has velocity, right? That velocity is changing because it's changing direction, but is moving with a relatively constant speed in a circle around the coffee cup. He seems excited. So some notes about circular motion. The speed is constant. If we're talking about uniform circular motion, the speed is constant, but the velocity is changing. Velocity is changing because the bird is changing directions. And remember that velocity is both speed and direction. So the speed is staying the same, but the velocity is changing. If we consider the direction the bird is turning, notice that the bird is constantly turning to the left. That means the bird is accelerating to the left. So the bird must constantly be turning towards the coffee cup, which is in the center of the circle. And what that lets us know is that centripetal acceleration, the acceleration that occurs for anything to move in a circle, always must be center seeking. That's what centripetal means. It always must be moving towards the center of the circle. Now, in order to move in a circle at the same rate, in order to maintain that rotational speed, the farther you are from the center, the faster you must be going. So if the bird wanted to finish its loops, its laps, in the same amount of time, and it were further away from the coffee cup, it would have to run faster, right? And if it were closer to the coffee cup, it would not have to run as fast in order to make those circles in the same period of time. Now, we can see this if we look at marching bands or we look at drill teams. Each of those at times makes gait turns. Let's watch this band, this Texas Tech group, demonstrate a gait turn.
Forward march, forward press, 1, 2, 3, 4, 5, 6, 7, place, close.
Now, did you notice that the young man on our left, who was the closest to us in the beginning, moved very slowly? He took very small steps as he moved around that corner. But the young man on our right, who was the farthest back in the beginning, had to walk much more quickly. Why?
Forward march.
Because
Forward press.
the young
1,
man in the
2,
front is
3,
very
4,
close
5,
to the pivot
6,
point,
7.
and
Place.
the young
Close.
man in the back was very far from the pivot point. The farther you are from the center of the circle, the greater your radius, the faster you have to move in order to rotate at the same speed. If we consider all four of these band members together, we could treat them as an object rotating. We're seeing the entire line, rotate. But each of them individually has speed, has their own velocity. And in order for them all to rotate at the same speed, the ones on the outside must have a greater linear speed. Again, we have rotational speed versus the linear speed of someone moving in a circle. They are all rotating together. They all have the same rotational speed, the same radians per second. But on the outside, they have to move faster in a circle. They have a greater speed linearly. Speaking of linear speed, so notice that if we have an object moving in a circle, that at all points its velocity is tangent to that circle. That's because at any point to move in a circle, you must be moving forward perpendicular to the radius of that circle. You are moving forward but turning to the left, just like that bird, right? Moving forward, turning to the left. So you have a tangent velocity. Remember, tangent means a line that intersects a circle only at one point. You have a tangent velocity, whereas you have an internal facing or a centripetal acceleration. So, how do we determine how fast something is going around a circle? Well, isn't velocity just distance over time? Displacement over time? Here we'll use distance, so we're technically getting speed, right? So the speed of someone at any point in going in a circle is the distance around a circle divided by the time it takes to go around that circle. Well, we know the formula for the distance around a circle, the circumference formula, 2 pi r. So how fast is the bird going around the circle? All we need to do is take 2 pi times his distance from the center of the coffee cup and divide by the amount of time it takes him to go in a total loop. So again, the speed of an object, the linear speed of an object moving in a circle, is 2 pi r divided by time. And the 2 pi r is the distance around the circle, and the time is the time it takes to go around that whole circle, because velocity is distance over time. But what about acceleration? We said that objects moving in a circle are always accelerating towards the center. Again, you can see here we have the tangential velocity, the linear velocity that's going tangent to the circle at every point as this object moves in a circle. But acceleration always points towards the center, towards that center point. Again, the bird was always turning towards the cup. So always turn towards the center, centripetal acceleration, in order to move in a circle. And our formula for this is that centripetal acceleration equals the linear velocity or tangential velocity squared divided by the radius. You can see a proof for that on YouTube if you have any questions about where that came from. But to make this short, the velocity matters more than the radius itself. It takes more acceleration exponentially as our tangential velocity increases. Let's talk about how this matters in your life. If you're driving a car and you go around a corner, If you are going twice as fast, your tires will have to accelerate you 4 times as much. If you go 3 times as fast, your tires will have to accelerate you 9 times as much. And remember, all acceleration is caused by forces. So that means you'll have to have 9 times as much friction in order to make that turn. Why is it so dangerous to drive quickly in the rain? Because when you have less friction available to you, the faster you go, the significantly more, the exponentially more acceleration you need, which is the result of more friction. So let's do a couple quick practice problems. Suppose we have a soldier. Okay, let's go over a couple of circular motion practice problems. So first we have a soldier marching in a circle. We know that the circle has a 3-meter radius and she finishes her orbit or her period in 8 seconds. So we first need to calculate the soldier's speed. What is our soldier speed formula or any circular motion speed formula? It is Vt equals 2 pi r over t. Again, what does each part of this mean? Tangential velocity, because anytime you're walking in a circle, your velocity is going in a straight line on the outside of that circle. It is tangent to the circle, it is perpendicular to the radius. Pi r, 2 pi r, is the circumference of the circle, and then t is our period. What is the period? It is the amount of time it takes to go in a full cycle. Again, the time it takes to go in a full cycle, in this case, going in a full circle. Let's plug into this our givens. 2 pi is all a constant. The radius is given as 3 meters, and our period is 8 seconds. Vt equals 2 times 3 is 6 pi over 8. That'd be 3/4 pi, right? So 3/4 pi. Let's pull a calculator real quick. 0.75 times pi gives us 2.36. 2.36 or 2.4 meters per second. We don't need to be super exact here. For our second problem, we're asked to calculate the soldier's centripetal acceleration. AC equals v squared over r. What v is this? Of course, this is our tangential velocity. So centripetal acceleration equals our tangential velocity, 2.36 squared, divided by our radius, which is 3. So AC equals this squared, 2.36 squared, divided by 3, which is 1.85. Let's call it 1.85 meters per second squared. That's our centripetal acceleration. Finally, we're asked to calculate the time it would take the soldier to go around half the circle, and this is just a basic velocity problem. If we have half the distance, then it will take us half the time, so it'll take 4 seconds. Hopefully that helps. If you have any questions, make sure you ask in live session.